So I want to tell you today about experiments that promise to change the way we understand and observe our universe. And I mean literally. Most of the things that we know about the distant universe come to us from light. Photons streaming from the edges of the universe to nearby objects tell us what those objects are, what they're made of. But light is not always the perfect messenger. There are corners of our universe that are dark, that are warped, and then we need a different messenger. And so today I want to tell you about this new messenger that we're trying to harness. This is gravity's messenger and is known as a gravitational wave. Now, gravitational waves were a very essential part of Einstein's theory of general relativity. But Einstein himself remained rather uncertain about whether they were really there, and certainly whether they would be measurable, because they're kind of weak. And I'll tell you more about that. But before we go on to thinking about gravitational waves, let me tell you what they might be useful for. So there are parts of the universe where there are objects, like black holes, where the gravity is so strong that even light cannot escape. How might we learn about those? We might have to use gravity itself to learn about those. So that's what my talk today is about. And what I'd like to do before we embark on this journey where we turn the lights out, we're going to think a little bit about what happens when we have light. Before I do that, let me talk a little bit about what you would imagine, information would we get if we turned the lights out in this room? What might we do to figure out what's going on around us? We would use our ears. We would listen for sounds. And this new tool of gravitational waves, we believe, is going to allow us to start listening to the sounds of the universe. But before we get to sound, let's think about sight. And we have seen incredibly spectacular things about the universe using light. This is a supernova remnant, Cassiopeia A. And it's a beautiful image taken with different colors of light. The red colors are infrared, which our eyes cannot see, but snake eyes could. The green and yellow colors are visible light, which our own eyes could see. If we could just look out into the sky and look at this object, we might see those colors. And then the blue and purple colors are X-rays. Now, all these different colors tell us different things about this object. What is it? Well, it's a star just like our own sun that exploded. When it ran out of nuclear fuel to burn, stars like our sun explode. And what we're seeing in this image are the ejecta from that explosion pushing out from the center where the explosion happened. The different colors tell us what the energies were for all these different ejecta. They also tell us what the content is of the material of the ejecta. Now, there's one little thing in the very center of this object which we should try to spot. It's a little blue dot. Now, this is a blue dot because it only shows up when we observe Cassiopeia A with X-rays. If we looked at it with radio waves or infrared or optical light, we wouldn't see it. And that tells us the importance of being able to see all these different colors of light. A blue dot. Why would that be interesting, you might wonder? Well, it's actually an incredible object which is born when stars like our sun die. It's a neutron star. A neutron star is a star that has about the mass of our sun, but it's crunched into a ball of radius 10 kilometers. Now imagine that. Our sun, 700,000 kilometers big, and you take all of that mass and scrunch it down into the size of a small town. That's a really dense and gravitationally compact object. And in regions of space where such an object lives, gravity is very strong and very warped. Now, if the parent star that exploded had been a few times heavier than our sun, instead of this neutron star being born in the center of this supernova remnant, it would have been a black hole. And in fact, that's how we believe some black holes are born. Now, how might we observe a black hole as it evolves in its life, as it grows and eventually dies, well, we better give up on using light, because eventually there'll be no gas and dust around this black hole for us to observe. It'll be sitting there in empty space and will be invisible to us if we just point our telescopes at it. But fortunately, space is not empty. Space, as Einstein taught us, is actually warpable. When we put massive objects into empty space, they warp the space. And in fact, when those massive objects move, we actually can get ripples from that space. All right, well, imagine there was a movie playing over here. What you would see is that if we lay a grid down on all of space-time, empty space, we just lay down an imaginary grid, we put a massive object in the middle of that, those grid lines, instead of being the straight lines we're used to, would start to distort and curve. Now, Einstein also taught us another piece of this. If you take that massive object, and instead of it just sitting there and warping space-time, if that object moves around, it wobbles, those space-times will not just warp, but they will form waves and start to travel outwards from that object. And that is a gravitational wave. It is actually the ripples of the space-time itself traveling outwards from the object. That's all fine and good. And that allows us to look for objects even when they give off no light. So here is then the movie I just described. You can see that as this object, the bright object in the middle, wobbles up and down, these waves travel outwards, much like if you dropped a rock on the surface of a pond. Now, keeping the analogy of the rock on the surface of the pond, as the ripples travel outwards from the rock, if you were a small little toy boat sitting somewhere at the edge of the pond, as that ripple passed by, you would bob. Hold that thought. Before we go there, let me now ask, what does the space-time look like when we approach a black hole? Now, black holes or neutron stars, they're born in kind of the same processes, just matters if their parents were about the mass of our sun or a lot heavier. They sometimes are born as twins. They form binaries. Even if they're not born as twins, sometimes they find another black hole and they get into orbit around each other. But these orbits are unlike any other orbits we can imagine, because these are very, very massive objects whipping around at relativistic speeds. So the space-time around such objects can be very warped, and in fact, that's what this movie shows. There are two black holes that you can see, and these black holes, towards the very end of their lifetime, are radiating these gravitational waves, which are all these different colored contours traveling away, and they eventually collide and form a single black hole. The gravitational waves carry away energy, and that energy causes the black holes to come in closer and eventually collide. This is a region of space-time that you don't want to be very close to, because you'd be ripped apart by these warpages. But they happen in the distant universe, and we would love to be able to observe them. Now, if you could take that picture I just showed, that movie, and turn it into a signal here on the Earth, what would you see? Well, you would see something like this graph over here. As promised, in the language Einstein used, in the language I'm using, it's a wave. So it has peaks and troughs that propagate with time. And in fact, general relativity allowed us not only to think about the shape of the wave, this shape is actually predicted by general relativity, it also allows us to predict the size of the wave. And that's the height of the peaks and troughs. Those are measured in units of strain, or a quantity h that we like to think about. And if you take a pair of neutron stars in a binary system that's oscillating around, that's orbiting around each other, and you put those neutron stars, they have about the mass of our sun, you put that pair of neutron stars in a galaxy not too far from our own, you can get a number for how strong the emission should be. What's the size of those waves? And that turns out to be 10 to the minus 21. Now, that's a small number, you'll all agree. But until we understand what the strain actually means, we shouldn't be too worried. So our next question should be, well, what does the strain mean? And to answer that, we want to ask, what does this gravitational wave do when it arrives here on the Earth? And what it does is it changes the distances between objects. It changes space-time distances. By how much? Well, if you have some distance L, it will change L by an amount delta L, and delta L is proportional to the size of the wave, the strain amplitude h, times the distance it propagates through. How might we put a scale on this? Well, let's think. I'm a space-time object of about 1 meter, my height. If a gravitational wave with this amplitude 10 to the minus 21 goes through me, it will change my height by 10 to the minus 21 meters. Okay, so now you should be truly horrified, right? I'm telling you that if the gravitational wave comes through an object about a meter long, it will change that meter by a millionth the size of a single proton diameter. Okay, so yet I started my talk by telling you that there were experiments where we wanted to measure this. Okay, so how do we do that? Well, we design our detectors. We turn the knob where we say, well, we know if we could make L, the space-time distance, larger, we would get a bigger effect. So we design detectors where we actually make the distance, the length of the detector, kilometers. So about 1,000 meters or a few thousand meters. And then we have the simple task of measuring these kilometer scale separations down to the level of 10 to the minus 18 meters. A whopping 1,000th the size of a proton. So I want to tell you, even though you must be very incredulous right now, that we do know how to do that. And that brings me to the observatories that have been designed to measure these passing gravitational waves. So gravitational wave observatories, like the ones that I've shown in this picture here, are scattered over the planet. The two that I've shown are the detectors, are the two US detectors of the Laser Interferometer Gravitational Wave Observatory. That's a mouthful. We lovingly call it LIGO. And what you see in this image is aerial views. Why aerial views? Well, because I promised you for this effect to be measurable, we have to make these path lengths rather long. So the principle of the measurement is that at the corner center where you see the building, we have a laser. And then in an L shape, along the two arms of the L, we propagate laser beams. They reflect off of mirrors 4 kilometers away. They come back to the center, and we measure the light travel time of those laser beams. Okay? And by measuring the light travel time, we can tell what the distance was. And we can do that with sufficient precision that we can actually tell changes of over 4 kilometers, changes in distances of 10 to the minus 18 meters. Now, it turns out that when you get to those kinds of scales, when we're talking about distance changes of 1,000th the size of a proton, quantum mechanics starts to matter. So here comes a gravitational wave. It goes through our detector. These tiny changes in the spacing between the mirrors and the lasers register at our output of our L-shaped devices. But to be able to measure those, we need a really good meter stick. And the meter stick turns out to be the laser light itself. But it turns out that at those scales of 10 to the minus 18 meters, it's not the perfect meter stick. And that allows me to then take you on a tiny little journey, a very exotic journey, into some of my own research over the last few years, where we take laser light and we try to make it better. Now, why is laser light not good enough to begin with? It's not good enough to begin with because light is quantized. It comes in packets called photons. And as a result, quantum mechanics, quantum uncertainty demands that the light should jitter. You can think of it as if you had a ruler where the tick marks of your ruler jitter about because of quantum uncertainty. If I ask you to measure even something macroscopic like the length of a piece of paper with a ruler that's jittering about, you'll not have a very good shot at it. Now take that down to the 10 to the minus 18 meter scale, not a piece of paper this big, but something unimaginably small, and the quantum mechanics of light really starts to matter. So we do experiments in our group where we take these wavy, curvy, jittery rulers, we pass them through some complicated apparatus, and we get very pristine, or not as pristine as we'd like, but more pristine rulers out of our laser light. So this little cartoon at the bottom actually shows what happens. You start off with the light wave, and the wave is actually kind of ununiform. You see that its peaks and troughs don't have the same height, and its timing, its zero crossings don't have the same spacing. We pass that through our device, which here I've just shown as this little black box, and out of that comes much more uniform light. You can see that the peaks and troughs are now no longer as random size. So we actually have to make this exotic quantum state of light, called the squeeze state, to be able to make these measurements at the precision that we would like in these gravitational wave observatories. Now I want to end by really showing you that this is a global effort. There are a number of observatories, the two of the US observatories, LIGO in the United States, two in Europe. There's GEO and Virgo, which is a 3-kilometer detector. There's a detector being built in Japan that's 3 kilometers long. They all have kilometers in size just so that we get the sensitivity we need. And there's even been proposals and a lot of study for a space-based observatory called LISA, which has a certain advantage. Real estate in space is cheaper, and that allows us to make the path lengths for LISA 5 million kilometers long. But that's far in the future. There are other ways to make these measurements, and I want to just sort of drive home that when this whole range of experiments succeeds, and we hope this will be within the next few years, all these detectors are now reaching unprecedented sensitivities, we will be able to, for the first time, listen to the sounds of the universe. We no longer need light. We literally will be collecting data where the signals that we collect for these detectors are in the human audio band. They actually will make sounds if we encode them onto a loudspeaker. And we hope to be able to start exploring those parts of the universe that are dark. Supermassive black holes are known to be at the center of almost every galaxy. We don't know how they form. So if we can start to measure the signatures of smaller black holes and start to understand how are they born, how do they evolve, how do they die, we can start to understand what are these objects at the centers of all galaxies. Now, even farther in the future, gravitational waves are an incredible cosmic messenger because unlike light, they actually go through everything. And as a result, what we can do is we don't really care about what's between the gravitational wave source and us as observers. They don't get jumbled up like light does. They really just come straight through to us unadulterated. So it allows us to look back into the very early universe. In fact, to the very first fractions of a second after the Big Bang. Light doesn't allow us to do that. Light comes to us only from 400,000 years after the Big Bang. So there are enormous rewards that we're hoping to get from these experiments that are now coming online. And I want to leave you with this last thought, which is that every time we've turned a new instrument and pointed it into the sky, nature has revealed astounding beauty and has presented us with new puzzles like nothing our imagination could come up with. So please stay tuned. Thank you.